From Chicago, welcome to 3 Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
All the small to medium organization who can barely afford a one printer and two operators to work with that, and they would like, how can we make our parts quickly and reliably? What are some of the quick to-dos in order to get us started?
That was Yash Parikh. Yash is a process engineering consultant at EOS North America. In this role, his primary responsibility is to provide guidance and support to EOS consumers in effectively implementing AM technology within their organizations. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast. Remember, you can listen to the show anywhere you download your podcast, including Spotify, Apple, Amazon, or Stitcher. Also, if you or your company are looking for materials qualification or general AM support, reach out to the team through our website or via email at info@3degreescompany.com.
Yeah, Ash, thank you so much for joining the show today. Excited for the conversation. We got to meet in person a couple of weeks ago at the NIST working group on data management. But before we get to that, I like to start out with all the guests on more personal level. So kind of where were you born? Kind of what were some of those early days like in terms of getting you on the path towards additive manufacturing?
Absolutely. Thank you, Mike, for having me. It was nice meeting you at NIST workshop as well. My name is Yash Parikh, and I am currently a process engineering consultant with EOS North America, and I'm based out of Austin, Texas. I was born and raised in a city called Valsad in the state of Gujarat back in India. So growing up, my both parents were professor. So I have seen them do the hard work of learning every day and teaching next day. And I have seen them completed their PhDs during my growing years. So I had a big influence of having a mentor in-house. And both were linguistic professors, so they taught languages. So I had to emphasize on making sure that my pronunciations and everything is correct in that particular language. And those were Gujarati and Hindi languages. And I have an elder brother, so who was like 5 years elder to me. And while growing up, he ventured to become a mechanical engineer, and that kind of influenced me to take the path of mechanical engineering. So while growing up, those were the days where I had almost like fascination of learning more about machineries and stuff like that, because my brother used to bring those parts, which were back then made on lathe machine. So he used to show me that. So this is the base material, and this is what we did with that. So kind of machining or machinery had that sort of influence on me while growing up.
So it's kind of seeing those parts like in person, like, oh, like there's more than meets the eye here. Like
Exactly.
Yeah.
And then some of the other fascinating aspects that he shared on mechanical side of things. Back then, the computers were not that powerful, so the calculations were needs to be done by hand mostly. So I have seen him like referring to the log books and stuff like that, design handbook to get into all the design calculations for spur gears and whatnot. So that those had my excitement going to learn more about engineering.
And what was that process like? Do you start kind of thinking about engineering in high school, or was that more as you got into college and university?
More. So in India, you have similar education structure as US, and then after your 10th, you choose either you want to go with the mathematics background or biological side of stream. So I chose to become engineer, and during those growing years, I had influence. As I said, my brother was 5 years elder to me. So when I was in about my 8th or ninth grade, he was already starting with his engineering. So I was mentored greatly by him, actually.
Awesome.
So during that 10th, 11th time frame.
And so when you started university, you're doing presumably mechanical engineering.
Mechanical. Yes.
Was it what you expected?
No. First year was completely different because now you got a thermal and heat transfer and all of those which is something you have not expected. More sort of a manufacturing side of thing. You were thinking for um, from mechanical perspective. I was like, oh, this is manufacturing focus. No, this is more sort of a heat, thermal, fluid mechanics. So it took me a while to figure out that it's a vast, diverse field within mechanical engineering itself. But eventually, I adapted, graduated uh, back in 2008 with my bachelor's from University of Pune.
Okay.
And then with my growing love for manufacturing, I actually pursued a master's in India from a university called VTU. It's in Bangalore. And then I specialized during the time in SIM, computer integrated manufacturing. So I stood university first rank during my master's. Had a 1 year project with Larsen and Toubro Komatsu, L&T Komatsu in Bangalore as a part of my thesis work.
And did you have I mean, your parents being professors, your brother being in the university, like, were you
Yes.
always kind of drawn to do more kind of like the academic track and like kind of continue on, or like it sounded like you had some pull to go into industry as well, right?
That's a great question, actually. And that actually happened. The moment I completed my 1 year internship during my master's, and the project that I was working on was on an excavator's capability improvement. The team actually offered me a job then and there, that if you would like to continue working on the project post your completion, please feel free to let us know. And at that time, I had a discussion with my father about whether to go for academic side of thing or stay in industry. And then he said, why not to try going into academics for a few years? And then I made a choice to be an assistant professor. I was about 23 years old when I was assistant professor in one of the universities in Pune, India. And back then, there was no requirement to teach for undergraduate to have a PhD at that time. So I chose that path.
How'd you like teaching?
Oh, it's absolutely fun. It's pleasure. I really love teaching. It's something that I learn from every interaction that I have with diverse population, and it enhances your understanding, in my opinion. So teaching something requires you to understand something first, in order to teach somebody else. So I think that's uh, that's a blessing to have.
And so around this journey, like when did you come into contact with additive manufacturing?
Great question again. When I was teaching, um, and I've taught for 5 years in India, and over the course of 5 years, I have changed a couple of institutions. So within these two institutions, I have taught roughly about 10 plus subjects. And these are undergraduate, graduate level courses, like your 300, 400 level courses, 600 level courses. One of the course was product design that I actually taught. And during the product design, there was a rapid prototyping. And back there, it was like, okay, you need to do a reverse engineering, and to get quick results, you have to adapt to 3D printing to get your rapid prototyping models done. And at that time, about 2012, 2013, I was like, okay, this is a really interesting technology. So that was my initial, and I did not know that it was called additive manufacturing back then. I had an impression of not even 3D printing, just rapid prototyping. That's what I heard back then. So when I was trying to search for different universities to pursue my PhD, I had no inclination to go into additive to do my PhD. It was more about mechanical engineering, and what I liked was product design. So it was like, okay, I'm looking for positions in these labs. And then interestingly, it happened that I got a mentor who was willing to take me and challenge me with the additive manufacturing aspects. And that happened because I worked on a project which had curriculum development on 3D printing. It was a position of a research associate when I joined the Texas A&M a college station. Um, and then that kind of project led me to be more excited about 3D printing.
And so what sorts of printing were you primarily looking at? Was it polymer? Was it metals? Was it a mix?
It was most, so the first 6 months that I worked on, it was a broad overview of all the 7 techniques of additive manufacturing, not particularly pinpointing any one, but I got a broad overview of, okay, this is what the umbrella looks like of additive manufacturing. And then I was excited to work on the laser powder bed fusion, actually, because we recently, Texas A&M had recently acquired Renishaw AM450, and they were looking for graduate students. So I was like, okay, I'll be the one who will be doing research on this platform. So it happened eventually that I was influenced by that sort of an external factor as well to choosing which technology within additive I would be working on.
And what were you like operating the machine? Were you like doing all sorts of stuff?
So initially we were not allowed to operate the machine. All we were able to do was prepare your CAD geometries, convert STLs, and send it to the operator, and he would be doing everything. But as we grew up in this position, and when you're like a 3rd year, 4th year PhD candidate, you have been allowed to play around with the machine a little bit more. But yeah, during that time also COVID hit. So there was a severe limitations as to how many students can touch the machine, highly touch surfaces, whatnot. So we had our fair share of experiences on handling machine in different conditions as well.
And what was your ultimate kind of research and topic?
So when I started, I was given an interesting problem, is to create a functionally graded structure from a single alloy using laser powder bed fusion. So at that time, ORN's Ryan D. Hoff and others have looked at these phenomena back in 2015. Actually, when I saw his paper, I was like, okay, those are some initial literature review that I did. It was a site-specific property that they investigated using LPBF, and then sort of that took my interest to a different level, as to let us understand the PV plot and understand the properties that you can get within the good zone without going into lack of fusion or any other defects, and explore what hardness, tensile strength, and fatigue properties and creep resistance and whatnot you can get, and can you stack those then on top of each other using process parameter manipulation. So it eventually took me a year, 2 year to get to a journey of exploring these PV space, and then eventually choosing correct parameters, correct properties for end application.
And so with that, I mean, maybe you want to talk a little bit about that experience, because I think it mirrors a lot of what happens in industry, maybe not so much from kind of functionally graded, but
sure.
A company gets a machine in, they're trying to go through the process of figuring it out, doing design of experiments, trying to capture like, what are we measuring? Is it tensile? Is it fatigue, to try and make a decision? So like, what are some of where did you start in terms of that journey, in terms of trying to figure out, okay, how do I even structure like what the and get to the question that I want to answer?
Yes. And that's a common question that happens with all the small to medium organization who can barely afford a one printer and 2 operators to work with that. And they would like, how can we make our parts quickly and reliably? What are some of the quick to-dos in order to get us started? And that comes down
buying
to
an EOS
other
machine,
than buying
right?
EOS machine, of course. And other than
Gotta get the plug in. Andy's going to be mad if you don't get that.
Yes, absolutely. And other than using the OEM supplied highly dense parameters. So
Sure.
what happens is you have to start looking at the end product uh, from a perspective of additive manufacturing. So what happens is, mostly when you're looking at conceptualizing a product, when you purchase a machine, you have something on mind that, okay, this is what I want to print. And conventionally produce, these are the XYZ properties of it. sometimes what happens is your realistic expectations cannot be met with additive if you're just comparing apples to apples in terms of property values. So you have to look around, play with processing conditions just to see that what are the design allowables given for uh, this particular material, this particular product that you are trying to build. So most of the time it comes down from starting from the least value and try to explore how can you go to the max value of that property. It could be tensile, say 700 to 900 MPa, something like that. And you try to reverse engineer and say that, okay, with this initial DOE, I was able to get up to 700 value of tensile strength. Can I play around and put more laser power or tune down a little on a scan speed? So you have to start with something in mind. You have to fixate your um, starting point on one single property. You cannot manipulate like 3, 4 parameters at the same time. That would lead to chaos. That would lead to unknown territories that you are heading into.
Right. And for sure. And it's prioritizing those parameters, right? Because tensile strength is one measure, but
is one measure.
Another, and like there's
absolutely
hardness and others that like it may not strength ultimately may not matter
exactly
versus another. Like it has to be a minimum, right? It can't fall apart, but like as long as you can look at it and say, okay, it stands up, but what are your other priorities? And for some people, like that may be challenging.
That is true. That is correct. And yeah, I mean, so those sort of experience of working in a different manufacturer's system, say Renishaw is what I've been trained on. When you switch on to a different OEM and now you're operating an EOS machine, things get changed pretty quickly. You need to know what are the different aspects of processing condition that are changed here. So can I say that? Can I fully replicate what I have found out on Renishaw AM450 on say M290? It would take me a while to reproduce these results exactly.
Do you think that's a good thing or a bad thing for the industry?
There's no straightforward answer to it, because at the end of the day, each manufacturer uses their proprietary settings and their proprietary third party. It could be a third party laser or a system like a build frame, gas flow. So what happens is in ideal world, it should have been like that what I've operated on, say a 400 watt machine, a different 400 watt machine using the same laser profile should give me a same value, but it eventually it doesn't happen. So it's bad that it's not happening like that. In my opinion. And that's how standards and other certification bodies come into this picture. So they are like, how can we make it more easy for operators who are switching jobs or somebody who is buying a new set of machines? Because every couple of years there's a revision in the machine, and companies are in additive going out of business and getting merged with another company. So they are producing a combined machine with 2 or 3 different OEMs coming together and stuff like that. So,
and so what? So you finished your PhD. What was your thinking after that? Did you want to go back to teaching? Did you want to go into industry? What was your thought process?
So during my PhD, I was able to do an internship at Oak Ridge National Lab manufacturing demonstration facility. So that has played a vital role in me choosing to go into research lab / industry, because I worked on a binder jetting during that 4 months of internship, along with laser powder bed and WAM, wire arc additive. And I was fortunate to meet a couple of greats in the field. Suresh Babu is one, and Ryan D. Hoff, Amy Elliott, Piyush Nandwana, and so on and so forth, Mike Karka. So discussion with them, and also I've seen how impactful the work is in whatever they do at Oak Ridge. I was fascinated when I got back and I had a year to defend. I was pretty much determined that I would like to go to a research lab position or do something in that space. So when I did my PhD, I completed my PhD in May 2021. I chose to do a postdoc actually. So I went to do a postdoctoral research associate position at Next Manufacturing Center at Carnegie Mellon. So I spent a year there, worked on a project on US Army Research Labs project on expedite manufacturing um, and point of need sort of scenario. And Professor Booth, Professor Rowlett were there as my advisors. So I spent 1 year over there, and then I had to figure out whether to go for academic route or choose an industry. And I guess I made a great decision to join EOS.
And what was that like? I mean, what from um, a interview perspective, did you know like what job you were, what role were you looking at? Because I think EOS has a couple different, like there's additive
Yes.
minds, there's like the machine building
Yes.
part. Like what
Exactly.
did you know what you were kind of going and getting yourself in for?
At that time, also the need I felt was that we need to come together on terms of qualifying the machines and as we are discussing before, making sure that they are interchangeable. The processes can repeat irrespective of who is the OEM over here. So at that time, I applied for quite a few positions, including R&D engineer and process engineering consultant. But I chose process engineering consultant mainly because of the role of qualification and certification that has been assigned here. So that took me on a different trajectory when I chose to go on a route of process engineering consultant. I was exposed to how EOS has been building their systems from like 30 years ago to till date. What are the different versions have come through, and understanding the nitty-gritty of each and every one of those. And I support both polymers and metals qualification at EOS.
And so, I mean, I don't have to go into great detail, but like, what
Sure.
do you mean by qualification? Because I think it's kind of like as a starting point, I think it's a catch-all for a lot of people. But like
No.
when you think about it, what comes to mind?
So my initial breakdown of qualification and certification is when a product is qualified, when you're trying to build a product or a part, it is qualified because it is meeting your design requirement. And that is as simple as it gets, that all the time you produce that part and it fits to your design requirements, what you have set across. When you want to certify it, you have to back those with different statistical evidence that you are submitting to a authority. It could be for aerospace FAA, it could be FDA in case of medical devices. Those are regulatory bodies that you seek for permission to certify that the part that you have produced meets the quality requirements, meets the expected specs, so to speak. So for me, qualification was how can additive parts, no matter where they are built on a build platform, it could be on the corner, it could be dead center, on a single laser. How can you make sure that without testing too much, you can reliably and repeatedly say that all of these are meeting requirements? And to get to that point, whatever steps you do, it all comes down to a qualification umbrella, so to speak.
Yeah, and I mean it's a topic that comes up quite a bit. We've talked with others on this. I mean, I think the conventional number that I hear often is usually qualification for a metal system's about a year to 18 months and $1.5 million.
Easy.
Is that fair?
That is correct. It is a fair assessment. That is correct. And we have a GE LEAP nozzle as a perfect example. 2015, they started printing these GE LEAP nozzle, right? 20 parts, they made it into one part. In 2018, they had produced 30,000 parts. And then by 2021, 100,000. But to get to that 100,000 repeatable, reproducible parts, they had invested millions of dollars. And you're right, it took them about 18 months to 24 months to get to qualification of their machines and lock down every single thing that they could control.
And I mean, we had this discussion at this NIST working group, but
Yes.
in your mind, the amount of data that you could capture for one of these systems
Yes.
is immense, right? Like even just in terms of things, the machine operator, the laser parameters, like you start making that list, it's could easily get over 100 variables pretty quickly.
Easy.
But is there a path to simplifying that? Is there a way that you, not getting any secrets away, but more just like how should people think about that without getting overwhelmed, right? Because we don't want to make the burden so high that you say, okay, here's a $750,000 single laser machine. You need 2 people. You also need a year and a half and $1 million to qualify it. And so like that makes the bar pretty high in terms of for what you guys want to do is sell machines, right?
Exactly. And that's how, if I'm talking about, I'll answer this in 2 halves, like generally and specific to EOS. So generally speaking, this process takes a while because you have to set together so many aspects which are involved in qualification, right from you have manufactured the machine and did a factory acceptance to installing at the customer site and doing a site inspection, and then making the machine within the specs by doing an operational qualification, and then doing a part of performance qualification. And then amongst this, there are facility readiness, operator side of personnel side of things. So it's a mammoth project, so to speak. But how can you leverage a data and make this process be a little fast paced? In this context, EOS has been making the printer since last 3 decades. So we know by running certain factory acceptance tests that this sort of model, say M290 on titanium with say 100 micron layer thickness, the repeated property would be within this range. So we leverage that by using the previous data, so to reduce the number of times you would require to run a particular build to say that this machine, this SI number machine is qualified.
Got it.
But to understand which data makes more sense within the terabyte of data that you extract from a build is also a very, very tedious work. The moment you put in situ aspects into this mix, it also creates its own data. And now you have tons of data and nowhere to look as a starting point, except because you have you have now changed laser power, scan speed, or you have kept it as is. What data from these different columns would you take to look into that? And by the time you do this, it's already a year or 2 year in the process and something has changed. Something new has been introduced in this mix. So can 5-year-old data give you a meaningful result if things are changed in terms of software upgrade, in terms of new laser, or a machine might have gone under a major revision in terms of maintenance? So it's kind of a situation where quick fixes have been introduced in terms of doing rapid qualification. We say expedite way of qualifying something, and that has been evidenced by use of data. That okay, we will try and test only 3 samples on the build plate, and the locations would be X, Y, and Z, and we'll do it repetitively. So Oak Ridge has now adapted a situation where on every single build they make, irrespective of what they are printing, they would print a small witness coupon at one particular location, and they'll track that for the journey of that machines, like 50 build, 60 build, 70 build, just to see from that coupon what is going on within the machine. So that's one way of understanding. So there are quick fixes which we can do.
And so with that, I mean, you said you work on both polymers and metals. Is one
Yes.
easy?
Yes.
Is one easier than the other, or is the process so similar?
Both are extremely different. The way you process polymer, it's a support-free printing in terms of polymer printing. There's no support structure, and you have the equal amount of complexity in polymer when you're looking at comparison with metal system. You're comparing it with both. Post-processing of powder is altogether a different ball game in terms of when you extract the parts, what you do with the thermally influenced powder, because every layer now, your entire powder is under thermal difference, right? So when I'm looking at these techniques, I'm like, okay, these needs to be made. Both of these metals and polymer techniques needs to be in a way that both are easily qualifiable. And so we typically do a qualification test on both our polymers and metal systems by 3 builds on 3 different powder lots. So it's
Sure.
nine builds in total.
Sure.
Yeah.
And we were talking a little bit beforehand about kind of some of your involvement in standards and the importance of kind of the even going from a Renishaw to an EOS system and vice versa. Like, what are your kind of thinkings, and how are you engaged with trying to help kind of rise the overall kind of adoption rate of additive?
That's a pain at this point for additive fraternity, as to we have these different machines. Can we make use of all of those to produce the same part, irrespective of you're printing it on SLM or Renishaw or EOS or Trump, for instance? So my involvement is in ASTM F42, 07, 06, 03 committees, and we are trying to discuss as to how to minimize the time it takes to qualify, but at the same time, the variation within manufacturer to manufacturer, what are allowables and what are something that you cannot compromise with. Meaning, you have a Gaussian profile in one of the laser from, say, Renishaw, and you have a top hat in, say, SLM, for instance. It all comes down to melt pool, right? So eventually you have to understand that whether to compare machine A versus machine B versus machine C, what is that minimum amount of tests that are needed to say that we can efficiently produce 316 on all A, B, and C machine without compromising. And it comes down to the powder. Now, each machine manufacturer has restrained the way that they allow certain powder to be used. So it's going there, but it is taking time as to making sure that the input feedstock stays the same in order to compare A versus B versus C, because different laser modalities, different gas flow patterns within the build chamber, and so on and so forth. So each manufacturer has a different signature. So we're trying to accumulate these, finding out that what is the allowable difference between A, B, and C that we could say that is approved, plus or minus 5%, plus or minus 10%. So, and it comes down to every OEM being open about it and also agree to share their data. So,
sure.
So to speak, yeah. So
awesome. And so, just a couple more questions.
Yeah, sure.
Looking ahead, we're about halfway through the year. What's exciting? What's on your radar for the remainder of 2023?
I am headed to MIT to give a talk on next month on about qualification on aerospace parts. That's immediate for me. There I'm planning on talking about how aerospace companies are looking into qualifying parts, but with the amount of time that they have, a very short span of time, how can we make sure that all the parts are qualified within a short span of time? Because the testing is what takes the majority of their time. It's not about printing the part; it is that getting it approved to be flight ready is taking a lot of time. Next, I'm participating in Solid Free Form that is happening in Austin, and Form Next is also in Austin. So I'm excited about both. I'm also headed to ASTM's ICAM. So those are a couple of things on my radar at this time.
Fantastic. And last question,
Sure,
a little bit
sure.
off the topic. What's a book that's had a meaningful impact on your career or your life in terms of sharing a lesson or kind of just a story you like?
It's called Thinking Fast and Slow by Daniel Kuhnman. And that book has given me a nice perspective as to when do you actually make a decision, an informed decision versus a decision that is more coming to you naturally. What are some of the areas? Because every other day we are coming across a situation where we require um, to make some decision which is changing the course of the action. So those are the decisions which needs a critical assessment. And reading this book, Thinking Fast and Slow, has given me that perspective. So I think that's a good book if you're into psychology as well.
Fantastic. Well, thank you so much for joining the show today. Look forward to seeing you at
Absolutely.
some of these upcoming conferences and talks and all that
Yeah,
you're doing. So thank you so much.
absolutely. Thank you so much, Mike, for having me. It was a pleasure talking to you. Great discussion. Thank you so much.
Be sure to check out our website, www.3degreescompany.com, for more content.